So yes, this is still the Euclidean week. We are still proceeding with the triangle geometry. So we'll be doing a paper from last year, November 2024, the national paper. And after that, we'll look at a question that was sent by Njapase, which is a little bit boxing if you ask me. So apparently it was written in Northwest last year, but it's a very good question. And remember, guys, the whole point in mathematics is to train you to think. And it's really unfortunate that they give you difficult questions in the exam and you're under pressure, like time. That's what I mean. So it means you need to train yourself to think fast. Well, I don't know how do you approach Euclidean. I think we can all agree that it's the king of paper too. So what I used to do was to do it at the end. After doing everything else, then I finish with Euclides. So that I know that even if I couldn't finish, then at least I got the easy ones right. So yes. But this is how it works in this case. I'm not going to write the statement once again. I'm going to read it for you. But what is nice is this is not like science. Yeah, no, you don't need to memorize everything I'll be saying to you. In any case, I'll be highlighting the most important things so you're not missing out. So this is how it reads. They say in this diagram, O is the center of the circle. Triangle PWS is drawn. So in other words, it's the triangle that is inscribed within your circle. I hope you understand what's the meaning of the word inscribe. It means you take a figure, either a square, a rectangle, a triangle, whatever, and you put it inside another figure such that the vertices of this figure will be on the circumference of the other one or on the sides of the other one if it's not a circle. For instance, let's say you have a rectangle like this and you decide to inscribe a kite in this rectangle. They could have used the word inscribe if they felt like saying triangle PWS is drawn, just to make you aware of the terminology. Okay, so yes, that's triangle PWS with vertices PW and S on the circumference of the circle. That's fine. Then they say OR is perpendicular to P. Yes, OR is perpendicular to PS. PRS is actually extended. It's produced to T. SW and OT, they intersect at the point V. Well, everything that they said is not really important except one thing, the fact that OR is perpendicular to PS. That's the only thing that is important in the whole of this statement. Another thing that is important is the following. They tell us that OV is to OT will be 1:4. That's what they say. If they felt like saying this is too much, they could have decided to say OV is to OT will be 1:4, like that. Two ways of expressing the ratio. And once again, we need to understand what's the meaning of the ratio. It doesn't mean the length of OV is 1 centimeter or 1 meter or whatever one unit. It also doesn't mean the length of OT is 4 units. But it means quite simply, if you take the length of OV and you divide it by the length of OT, the simplest fraction that you get is 1/4 because things will cancel out there. That's really important. Okay. So this is what I'm going to do right away. I'm just going to go to my diagram and say OV is actually from here to there. So I'm just going to let it to be K units because I don't know what is OV. But then they also give me OT, which is the total from here to there. It's 4, but I'm just going to say it's 4K. However, I can choose to only focus on this small part and say it's going to be 3K. Yes, VT is 3K, OV is K, but the entire OT is 4K. That's fine. Now we can begin and say, what are we given? And well, maybe before we can go to the question. So what can we see here? It's often helpful for you to identify all the theorems that you see and everything else which is not a theorem, but which can assist you. For instance, we know that if O is the center, then these two lines or sides, they are the radii and they're equal to each other. That's not a theorem, but it can really help you sometimes. You never know. Well, that's the only thing which is not a theorem, but we do have a theorem here. We know that PW is a diameter, and the angle subtended by the diameter at the circumference of a circle, we know that it is 90 degrees. That's awesome. We don't have parallel lines. If we know that this side is parallel to that side, or at least this line is parallel to that line, then we know that we can use the proportionality theorem, but we can't use it for the time being. But there's also another theory or a theorem that we see here. What is that? Well, this is a chord, PS. And this one, it is not a radius, no, but it is the line from the center. The line from the center is perpendicular to the chord. Well, can anyone tell me what does this line do to the chord? You can just go ahead and turn on your microphone and tell us. So it means no one is willing to speak. That's okay. We can always do this the easy way or the hard way. So we tried the easy one, no one answered. What do you think, Lebuse? What does this line do to the chord if it's drawn from the center?
Yeah, sir. Now I don't know, sir.
You don't know, sir.
No,
Okay,
sir.
so what do you think, Mamusadi?
I'm also not sure.
You don't know. Okay. What do you think, Mashata?
Say I don't know.
You don't know. Okay. So what do you think, Chikukulumese?
So I'm not sure, but I'm assuming it makes it perpendicular
It makes it perpendicular. It makes the
because
chord perpendicular. Is that what you're saying, sir?
yeah, because it's a 90 degrees by R.
Okay, no, that one is already given, sir. The question is, what does this line from the center do to the chord?
Yeah, I'm unsure.
Okay, so what do you think, Mavilagazi?
So I also don't know.
You don't know. Okay. So what do you think, Machabalala?
So I think it bisects the chord or the line PS.
It bisects the chord. Thank you so much, Elsie. Yes, the line from the center, perpendicular to the chord, bisects the chord. That's actually a theorem from centuries ago when you were still young, back in grade 11. So all your grade 11 theorems, you really, really, really need to know them. They are terribly important. Okay, thank you so much, Elsie, for that. I think that's all for this one. So we can go on and answer the questions. So what is the first question saying? Well, they say to us, please prove, of course with reasons, that OR is to WS will be 1:2. Well, the question is, which sides are those anyway? Well, this is OR and this is WS. In other words, prove that OR is half of WS, or WS is twice as much OR. That's what they're asking from us. Well, of course, there are many ways to kill a cat, yes? But I really suggest that you choose the easiest way out. I don't know which one is the easiest way, but the one that I'm going to do, I consider it to be an easier way, at least. So here we can see that we can actually prove that by using the midpoint theorem. I think it's the easiest we can use. What does the midpoint theorem say? Well, there's actually two ways of stating the midpoint theorem. I'm going to tell you the first way now, and in the next question, I'll tell you the second way. Not in this diagram, in a different diagram. You'll still have to state it, you'll see. Is it in a different diagram? No, in the same diagram. Okay, but in a different question. That's fine. Now, this is what it says. It says, the line segment passing through the midpoint of one side of a triangle parallel to another side bisects the third side and is equal half. Well, it's equal half of what? It's going to be half of the side that it is parallel to. That's what I'm trying to say. But in this case, we don't really have the parallel lines, no? So which is why we need to know the second way of stating the midpoint theorem. I think it's used to be called a converse in grade 10, but now I see when they use it, they just say midpoint theorem. So what does it say? It says the line segment joining the midpoints of two sides of a triangle is parallel to the third side and is equal half the length of the third side. In other words, in this diagram that we see here, we can now see that OP is equal to OW because they are radii. And Nosipo just told us that PR equals RS. So then, according to the midpoint theorem, this side must be parallel to that side. Well, in this case, we don't really need the parallel lines. But the most important thing is this side will be half of that side. That's what I'm saying to you. And I think it's the easiest way in this case for you to prove it. But of course, there are many ways. So let's go ahead and put it in black and white. Well, we tell them the obvious. Well, not really the obvious, but the obvious. So we say OP is equal to OW. Okay. Then we tell them that PR is equal to RS. And what's the reason for that? Well, this is the line from center perpendicular to the chord. That's theorem 1 in grade 11. The line drawn from the center perpendicular to the chord bisects the chord. Okay. Well, if you like, you can conclude and say, therefore, you don't need to include the parallel line. No, you don't. You don't need to, because it's an end. It means this one is parallel to that. And furthermore, this one is half this one. So when you say that, please tell them that you're using the midpoint theorem. You don't need to say converse, just say midpoint theorem. They are really going to be happy. And now you can rewrite it nicely according to what the question was saying. So you can now say, therefore, OR is to WS will be 1:2. I think this is the easiest way to prove it. It really is. So yes. So then, what is the next question saying here? Well, this is what they're asking from us. They say, please calculate the length of PT. It's a very beautiful request. Find the length of PT if it is given that the length of ST is 15 units. All right? So where is PT anyway? Well, this is where PT is. It's the entire length. So it's this total length. That is your PT. That's what we need to find. But then what is it we are given? We are given ST. It is 15. Well, that's not a problem. We know this one is equal to that one, so it can be easy to find PT. But the question is not really the question. In order for us to get to PT, we need to find first RS or PR, any one of those two. That's what we need to find first. And we can't use this ratio that we just got. It's completely irrelevant. It's just concerned with these two sides. So no. So what we need to do here is to look at this triangle that contains the parallel lines. We know these lines are parallel, but it's still necessary for us to tell them officially. Because according to the midpoint theorem, now that we have proven this, then the two lines are parallel to each other. It stands to reason. So we know these two ratios, that's awesome. Then it means it's now easy to find RS. So let's go. And I think we should enclose this one here to show that we are doing something that is brand new. How's that? Yeah, I knew you would agree. Okay, let's go. So this is the first thing we need to begin with. Let's convince them that the two lines are parallel to each other, and therefore we have every right to use the proportionality theorem. So we can say OR is parallel to WS because of the midpoint theorem. However, you don't really need to say this. The reason why you need to say this is if you're going to use the reasoning that I like. Line parallel to one side of a triangle. But you can also use the reasoning that says proportionality theorem. I'm not sure how it is written this part. You just say prop or what? I'm not sure. But if you use proportionality theorem as a reason, you must treat it as when you're saying alternate angles corresponding co-interior and tell us which sides are parallel to each other. If you just miss this one out, I think they can mark you wrong. So you decide what to do. So now that I have shown them that the two sides are parallel to each other, it's now easy for me to get to the point. I can now say, okay, fine. If I went to this nice triangle, this one, well, this is what I'm going to say. If I take OV and I divide it by VT, then I'm just going to get the same as when I take RS. I divide it by ST, while using the reason that I like. Of course. So what? We know that OV is 1K and VT is 3K. So this means RS is to ST will be 1/3. Okay, like that. Then we remember something. What is it we remember anyway? We know that the length of ST is given to us as 15. And when you do the math, when you cross multiply here, RS times this, it's 3RS, which is equal to 15. And dividing both sides by 3, we find that the length of RS will be 5 units. All right? Well, in case you're a little bit confused, OV is to VT. That ratio is 1:3. So I just decided to say, okay, fine. Where I see ST, I'm just going to put a 15 there. So that's just it. I wanted to get straight to the point. Okay. But that's not what the question is asking from me, no? Then now I come back and say, okay, fine. I want to get to PT, but this is what I'm going to say. I'll say, I know that RS is equal to PR, and both of them are 5 units. Well, the reason here is it's already been proven above. This is how you proved it. The line from center, perpendicular to the chord, bisects the chord. Which means if this one is 5 units, then this one is going to be 5 units as well. But then what does it say about the entire length of PT? Well, you take 5, you add it to 5, you add it to 15. And you find that PT will just be 25 units. Yes, I think this one was a little bit of a nice warm-up, if I can say. Yes, because these two questions, they come from the same paper. So here, they were asking you to do some push-ups for the real deal, which you'll see shortly. So once again, I'm going to read the statement to you. This is what they say. They say, in this nice diagram, A, B, G, and F, they lie on the bigger circle. Of course, you can see them. Now, furthermore, A smaller circle, which is the pink one, is drawn to touch the larger circle internally at the point A. Well, two circles touching internally, it really means nothing in Euclid's geometry, but it's something in analytical. But nonetheless, that's fine as well. Then they say EA is a common tangent for both of these circles, and EBCF is a tangent to the smaller circle at the point C. AC is extended to G. AF cuts the smaller circle at D. AB, CD, and GF are drawn. Well, what is the important thing in this case? What is important is EA is a common tangent. EBCF is a common tangent. In fact, it is a tangent to the smaller circle at C. Sorry about that. That's just the only things that are important. Everything else, even if you didn't know it, you can still get all the marks in this question. But nevertheless, let's go ahead. So once again, we want to identify all the theorems that we see and everything else which is not a theorem, but which can assist us. Those small things, they can save you sometimes. Sorry. So let's go. Well, the blue lines that you see here are tangents. And I think you know me by now. Every time I see a tangent, I quickly run. So if I go to the smaller circle, the angle between a tangent to the circle and a chord, that angle is equal to the angle in the alternate segment. So that's just what I'm going to say here. I say, okay, fine. A1 plus A2, and you know I don't like calling angles that. It's not wrong. I just prefer to say angle EAG or EAC. Yes. That angle will be equal to angle D1. So here I'm looking at the tangent and the smaller circle. All right. Now once again, the angle between a tangent to the circle and a chord. Now I'm looking at the bigger circle. In other words, angle A1 will be equal to the angle in the alternate segment. So meaning angle A1 is equal to angle F1. That's what I'm saying to you. All right. Now let's move or rather shift our focus and go to the other tangent, EBCF. So what do we say when we get to this one? Well, the same thing. The angle between a tangent to the circle and a chord, C3, that is to say, will be equal to the angle in the alternate segment. So we know that this one and that one are equal to each other. Is it all? Of course it's not. The angle between a tangent to the circle and a chord. So in this case, what am I saying? I'm saying this angle here, C1, will be equal to the angle in the alternate segment. In other words, C1 here is equal to angle D1. Well, that's what we can see. Now, is it all for angles which are equal to each other? No, it's not. Which one again? Well, if you look at this one, the very same angle A1 plus A2, which is EAG, that angle is equal to the angle in the alternate segment like that. And furthermore, this angle and that angle are equal to each other because they're both subtended by this arc or the chord, if you like. Well, not really if you like. When I say if you like, I mean you have a choice. Well, you do have a choice. You can use a chord or you can use an arc. You decide. But bottom line is there are angles in the same segment. Then from this point, I think other things can be like exterior angle of a triangle. For instance, B2 is an exterior angle of this triangle. Yeah, things like that. So those are additional things that you should be aware of. Now, I think we'll stop here with the analysis of our figure. Hopefully I didn't corrupt it. Okay, let's go. So what is the first question saying? Well, it says, if it is given that angle EAG is equal to X, determine with reasons 4 other angles that are each equal to X. And this is for 6 marks. Okay, fine. What are they saying? Angle EAG is actually A1 plus A2. Now we know this angle is equal to X. That's fine. Now right away we know that angle EAG, it's now time to write them down. We are done identifying that. We did it centuries ago. So we can now say angle EAG is actually equal to angle D1, and both of them are equal to X due to the tan chord theorem. Well, we'll write it in full. That's fine. Is it all? Of course, it's not all. We know that angle C1 is equal to angle D1. And of course, since D1 is X, then it means C1 will be X as a result. Well, for the same reason, tan chord theorem. Is it all? Of course, it's not all. We know that once again, angle EAG, but the blue one this time, it's still the same angle, just that I use the different label, of course, will be equal to the whole of angle F. Even though when you say F here, it's still acceptable, but you know that a mathematician is very specific. So please call it angle AFG. And of course, it's for the same reason as well. It's due to the tan chord theorem. And this one, you might have missed it. It's really, really easy for you to miss it. Now, which one is that? It can be easy for you to lose sight of the fact that you are having an X here. And each time you have an X, you know that these two angles are equal to each other because they are horizontally opposite. No, we don't have horizontally opposite angles. Vertically opposite, yes. And of course, these two are equal to each other as well. They are vertically opposite as well. So that's what we are saying. So now we can say C1 equals C4. And of course, both of them are equal to X. That's because they are vertically opposite angles. And these are the four angles that are each equal to x over and out. So then what does the next question say now that we have obliterated this one? So here they say to you, please do the following. They say, prove that when you take AG and you multiply this by AD, you are exactly going to get the same thing as when you take AC and you multiply this by AF. Well, this is what we are given here. Okay, fine. So my question here is, do we need to use similarity? Well, the answer can be a yes. It can also be no. Now, why am I asking this question? That's because the question that follows this one says, prove that triangle AGF is similar to triangle ABC. Well, this is what the question is saying. Well, since we can see that it's raising some eyebrows, then the question becomes, if we didn't want to use similarity to prove this, what can we use instead? That's a good question. Well, that's when you realize that AG is this entire length, all right? AF is this entire length, all right? Now, furthermore, AD is this second longest length, and AC is this second longest length as well. So this means you don't really need similarity. You can use the proportionality theorem in order to prove this, yes? Unfortunately, you don't have parallel lines because these two lines must be parallel to each other in order for the proportionality theorem to hold. Well, what is unfortunate is about to become fortunate because it's actually possible for you in this case to prove that the two lines are parallel to each other. The question is, why would it be possible anyway? Well, let's test. No, let's not test you, I'll see. We'll see you some other day. So yesterday I assigned here a homework to go and find how do you prove that two lines are parallel to each other. So hopefully she did her homework and she found that if the corresponding angles are equal to each other, then the two lines are parallel to each other. You could have done this or you could have just used similarity. That's perfectly fine. When you use similarity, it means you're going to prove that triangle ACD is similar to triangle AGF. I think we should do both of them. No, let's do both of them. I just realized something. Let's do both of them, all right? Fine. But firstly, we are going to do it the way that I want. And what is that? Using the proportionality theorem. We know that angle D1 is x. Angle F is also x. So those two angles, they would be corresponding if the two lines were parallel. So this means I can simply say, well, I tell them what I see. I say angle D1 is equal to angle F, which is AFG. And what could be the reason? Well, they are both equal to x. So what? Well, this means the line CD is indeed parallel to the line GF. Why? Well, that's because corresponding angles are equal. This is the reason you use when you prove that lines are parallel. But if the lines are parallel, you're going to say corresponding angles because CD is parallel to GF. This is just a proof, actually. It's the converse of that thing. Okay. So now we know that two lines are parallel. Then I can just state the proportionality theorem. I can say, if I take a smaller length, which is AC, I divide it by a whole length, which is AG. This will be the same as if I take a smaller length, which is AD, and I divide it by a whole length, which is AF, like that. And then I can give a reason, which is the reason that I like. Line parallel to one side of a triangle. So this is what we say. Then it's now time for us to cross multiply. And when we do, we just realize that AG times AD will just be AC times AF. Yes, this is what we can say, and then we are fine. Well, the second way in which we could have proven this was to use similarity. So how can we do that? I'm just going to erase this part here. But we are now going to work. Every question we'll be doing henceforth will now be using the fact that the two lines are parallel to each other. Of course, where it is necessary. So, yes. Okay. If we have to use similarity in order to prove this, then we know that we need to begin by locating the triangles. That's what we know. And how do we locate the triangles? We just need to divide both sides. So let's say we divide by AD, and we also divide by what? Anyone is fine. AF. So, well, on the left-hand side, we'll be having AG in the numerator, AF in the denominator, AC in the numerator, and AD in the denominator. Right. Now we managed to get this to a ratio. Then we try to read vertically and say, does triangle AFG or rather AGF exist? Well, let's go and see. This is A, this is G, this is F. Yes, it does exist. We come back again and we read vertically once more. Does triangle ACD exist? Yes, it does exist. Now, seeing what we see, then we are just going to come and say, in triangle ACD, which is the much smaller one, and triangle AGF, the following is happening. We can see that angle A is a common angle, but it does have a name, and the name is A3. So A3 is set equal to A3, while that is a common angle. D1 is equal to angle AFG. Well, they're both equal to X. So that's the reason for their equality. Yes, you can say they are both equal to x, or you can say, what else can you say anyway? You can choose to say they're both equal to EAG. That's fine. Yeah, no, I think it's much safer to say that. EAG. Well, anyway, even if you just say X, it's still perfectly fine. You found another angle which both of them are equal to, and they will be equal as a result. So yes. Well, then this stands to reason that angle C2 must be equal to angle G because of the sum of angles in your triangle. And now you can conclude and say, well then, this means that triangle ACD will indeed be similar to triangle AGF. All right? So now that they are similar to each other, then it's now time for you to go for the corresponding sides. Now, which sides are corresponding in this case? That's a good one. We know that you go to the angles that are equal to each other, and you say the sides opposite those angles must be corresponding. But in the ratio that we are trying to prove, we can see that CD and GF are not there. So you can choose to omit this ratio. Then shift your attention. Angle G is in the bigger triangle, and we know that it's equal to angle C2, which is in a smaller triangle. So then if you take AD in the smaller triangle and you divide it by AF, this will be the same as what? Well, you now go to these ones, you say, I can erase that, no? You say this one is opposite this side. This one is opposite that side. Taking the smaller length, it's AC, and it's divided by the entire length, which is AG. The reason why these corresponding sides are in the same proportion, that's because the two triangles are similar. It's the reason why. Then now you can do the cross multiplication and find that AD times AG will be equal to AC times AF. Any of these two, you could have decided here and beat length. So in this case, this is what they say to us for 4 marks. They say, please prove that triangle AGF is similar to triangle ABC. All right? It's a very straightforward question, which is fine. So where is triangle AGF anyway? Well, let's go and find it. It's the bigger triangle, so I'll just let it be green. Well, yes, that's the triangle. And furthermore, we have, where is ABC? Well, ABC is really an introvert. So this is where it is. This is A, B, and there is your C. Well, that's fine. Okay, fine. Let's begin. So we tell them that we are focusing in the bigger triangle, which is AGF. as well as in the smaller triangle, which is ABC. Yes? Now, what is happening in those two triangles? Well, we already proven that C1 is equal to C4. We said they are horizontally opposite angles. All right. Then what else? Well, in this case, we have A2. A2 is not X. Remember that. X is the entire EAG, the entire angle. That is X. Please don't be misled by that X. Okay, fine. We can also see that angle B2 here is indeed equal to angle G because they are angles in the same segment. They are subtended by the same chord. Or, so yes, B2 is equal to G, angles in the same, well, you'll finish this segment. So then, it stands to reason that A2 must be equal to A3 due to the sum of interior angles of a triangle. Of course, you'll finish that as well. And therefore, these two triangles, they are lookalikes. And you purely used the angles in order to prove this similarity. And that is that. Thank you, sir. Thank you, sir. So here I used wrong angles. It wasn't supposed to be that. C4 is in this triangle. I'm really sorry about that. What I should have said is C1, must be equal to angle F there. That's what I should have said. Thank you so much, sir. And we know that angle F is simply AFG. Yes. Yes, sir. Thank you so much for that. So yes, this is X and that one is X as well. That's what I should have said. Thank you, sir. Okay, so since we haven't got further questions, then let's jump straight to the next one. What does it say anyway? Well, it says, please prove to us that the square of GF is actually equal to BC times FC times AF, and this is divided by AD. Yeah, this is what they say. And how many marks is this anyway? It's 6 marks, imagine. So how do we actually prove this? It's a very good question. The first thing we need to do here is to use our similarity. Let's try to see that from these two triangles, can we get anything that is situated or rather found in here? That's the first thing we want to do. Anyway, we can see that it's really impossible to try and locate triangles in this case. We have many sides, GF, BC, FC, AF, AD, imagine. So it's really impossible to locate two triangles. So when you see that it's impossible to locate two triangles, it means you may have to use similarity and the proportionality theorem in the same question in order to end up having this complex monster. Or you might have to use similarity and similarity of another triangles as well. It's really, really possible. It's very, very rare whereby you'll get this thing in just two triangles which are similar to each other. You'll have to think a little bit out of the box, all right? Well, you also have the proportionality theorem, so not bad. I just want us to begin by stating the corresponding sides because I'm going to erase the top part, all right? Okay, so let's go. Well, when we go here, what do we say? Well, we can see here that this side AB corresponds to this side AG. So I'm going to write it here and say the smaller length AB divided by the bigger length AG must be set equal to what? Well, we shift our focus and then we say angle G. We said it is indeed equal to angle B2. So this means taking the smaller side, that is AC, dividing it by the bigger side, that is AF. And this in turn is equal to what? Let's write all three of them because we haven't made a connection yet. We are yet to think. So well, we said A2 equals A3, which means these two sides are definitely corresponding. So if we take BC and we divide this by GF, right? So that's actually where we begin. That's where we begin when we write our thing nicely. But now we know that we can write, or at least we don't have to write all three of them. All three of what? The ratios here. We just need to choose two of them which are relevant to what we are given here. So let's choose. So we do have BC here. All right. We have GF. We do have it even here. Do we have FC? No, we haven't got it. Do we have AB? No, we haven't got it. AG? No. So it means we drop this ratio out. Why do we drop that one? It's a little unfair because we still, okay. What is this anyway? AF, right. This is AF here. Sorry about that. So if this is AF, even though AC is not there, but we are definitely taking this one that has an AF in it. No, we are definitely taking it. AB and AG, they don't appear anywhere here. So we drop that. All right. That's the first thing we officially write. We say BC over GF must be set equal to AC over AF. Now, why are the corresponding sides in the same proportion? Well, that's because the triangles are similar. But you know that I like to specify unless space is really putting me in the corner. So triangle ABC is similar to triangle AGF. Right. Well, since we have GF squared here and we see that GF is the subject of the formula, then let's make GF the subject even here. How do you do that? You cross multiply. So you get BC times AF, which is set equal to AC times GF, which means that every time you see GF, you actually see AF times BC, and this is divided by AC. Yes, this is GF as the subject of the formula, all right? Okay, fine. Now it's time to think. Where to from this point? That's a really good question. Now we check. So here we can see that AF is present, so we are good. We do have AF here. We have it there. We do have BC here. We have it even there. We just don't have FC in the numerator and AD in the denominator. Instead, we have AC. So how can we make a plan here? Firstly, where is this FC? That's the first question you ask. Well, if you look at FC, you can see that, it's not in these two triangles, which I have proven to be similar. That's what you see. It's that red side there, which is not in any of those two triangles. Do you see that? Okay, fine. So then, how can you end up getting FC? That's a very good question. Well, we can't really get it even from the proportionality theorem. So this means we have to prove another pair of triangles to be similar to each other so that we can get the corresponding sides from it. But the question is, what is that pair of triangles which we need to prove to be similar? Well, I want you to realize that if you were to look at triangle CGF as well as triangle ACD, if you were to look at these two triangles, you would be able to realize that they are similar to each other. What am I saying? This is angle x there, or rather it has a value of x, has a value of x. What is another thing which is similar? Well, let's think a little bit, or at least, in fact, the angles, I mean, not similar, but equal angles. That's what I should have said. Well, let's see. Now my diagram is not too messy. I can still see clearly. So why can't I see clearly now? Yeah. Because why do I want to prove those two triangles to be similar to each other anyway? Well, that's because I can get to have the side FC. Yes, I can get to have the side FC. I can also get to have the side AD. So the two sides which I don't see in this ratio yet, I can get to have them if I were to prove those two triangles to be similar to each other. Okay, fine. I think I should prove them to be similar. So let's go. Yeah, no. Don't worry, guys, you haven't done a lot so far. So far, you only stated this and then you made GF the subject. It's a 6-mark question. It's worth working for. So we say in triangle ACD, as well as in triangle CGF, what is happening? We already said something here. We said angle D1 is equal to angle C4 because they're both equal to x. So we can say that that's perfectly fine. Now, what is another thing? Well, here we need to make a connection. It's not so straightforward. We know that these two lines are parallel to each other. So now we can get to have the alternate angles. So what does it mean? It means this angle C3 here, it will be equal to this angle, which is F2 there. But how does it relate to the other triangle? We haven't lost sight of the fact that this line is a tangent. And so the angle between a tangent to the circle and a chord is equal to the angle in the alternate segment. That's the connection we are trying to make here. So I guess that's how we can begin, and we can say angle C3 is equal to angle A3. This is due to the tan-chord theorem. But angle C3 is equal to angle F2 because they are alternate angles. And the reason why they alternate is because CD is parallel to GF. So think of it. What are we saying? We are saying this angle is equal to that, but this one is equal to that. So what's the conclusion? The conclusion is this one must be equal to that one. Yes, therefore F2 must be equal to A3. Okay, now we have proven two pairs of angles to be equal to each other. Then this means angle C2 will simply be equal to what? To angle G, due to the sum of angles in a triangle. Right, we'll finish that. And now we can conclude and say, well, this means these two triangles are similar to each other because we purely used the angles. Okay, fine. So now the two triangles are similar to each other. So what? Then it's time to come up with the corresponding sides. So let's do that. How do we come up with the corresponding sides? Well, I'm just going to write all three of them down here so that we come up with, or rather we only focus on the relevant ones. Okay. We said A3 is equal to F2, which means the side CD. Okay, no, I'll just write it here and then go to the next page. I think I'm forcing things. Yes. The side CD, which is opposite the angle A3, corresponds with the side CG, which is opposite angle F2. Okay. So I chose to begin with this triangle and then go to that one. That's fine. We also know that D1 is opposite AC and D1 is equal to C4. So this one corresponds with GF, which in turn is going to have what? Be equal to what I mean. It will be equal to AD, which is opposite A2. And this is divided by CF, or rather FC, Well, they want it as FC, so let's say it as FC. And since this one is not in what we are trying to prove, we can just let it fall away and focus on those two. But the question is, how do we focus on these two? That's a good question. I'll just go to the next page and write down here what we are trying to prove. We are trying to prove that GF squared equals BC times FC times AF. And this is divided by AD. This is what we are trying to do, all right? But now, what about, okay, I'm just going to write the findings from previously. Firstly, let's remember what is GF. We said every time we see GF, firstly, we see AF, BC, AC. AF, BC, AC. Hopefully it's correct. AFBC AC, right. Now we have found that AC over GF yes, we have just found that AG over, wait, C actually, GF is equal to AD over FC. Yes, AD over FC. So this is what we are saying, right? And then we'll give a reason and say that's because the two triangles are similar, ACD and CGF. Okay. Then the question is, what needs to go and what needs to remain? That's a good one. Well, let's see. We don't have AC. So this means we need to make AC the subject and substitute it into GF. That's what it means. And how do we make AC the subject? That's easy. We cross multiply, so we get ACFC, which is ADGF. And if you now make AC the subject, you find that AC is actually going to be ADGF divided by FC. That's what you're going to find. Yes, ADGF over FC. That is our AC. Then what? What is GF then? Now we are going to substitute AC, all right? But you can do this in a rather intelligent way. You can say, here we have AF multiplied by BC. And instead of you saying divided by AC, multiply this by the reciprocal of AC, because you don't want to have a horrible fraction at the end of the day. You are running away from division, dividing another division. So, what? Well, you now have your AF, which is multiplied by BC, and you multiply this by the reciprocal of AC. It means you take FC, you put it in the numerator. You take AD GF and put it in the denominator. That's how it works. Then you can multiply throughout by GF. Yes, you can multiply throughout by GF, even on the left-hand side by GF. So that GF times GF, it is GF squared. And in the numerator, you have AFBC, FC, divided by AD. Yes. So that's that. It may be necessary to prove another pair of triangles to be similar to each other, and then you can take it from that point. So these are the high order questions in Euclid's. Yes, no, they just need practice, 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 and a lot of understanding as you get your solutions. Build your experience so that you can, yeah, man. Yeah, I know you get what I'm trying to say, but that's what I'm saying. Right. They say in this diagram, D is the center of the circle. BF is the tangent that touches the circle at a point B. Then they say C lies on the circle to form the chords AC and BC. Then D is joined with F and BE. Yes, BE, which is this, is equal to DE, which is that. Right. That's all you need to know. So the most important thing from the statement is D is the center, BF is the tangent, DE is equal to BE. That's the most important thing, all right? So then, what does the first question say? The first question says, prove that angle C is equal to angle ABF. And this is for 4 marks. In other words, prove that angle C here is equal to angle, ABF, this angle there. Well, this one is really a walk in a park. Now, if D is the center, then BA, or rather AB, is a diameter, and therefore angle C will be 90 degrees. Well, it's an angle in a semicircle, you can do that. But then if AB is the diameter, then DB is a radius. And if BF is a tangent, then it stands to reason that angle ABF is also 90 degrees. Because a tangent is perpendicular to the radius. All right? Now you can conclude and say, well, this means angle C is indeed equal to angle ABF. And if you like, you can say they're both equal to 90 degrees, but you don't really need to say that. It's obvious, we can see it. So the most important thing was to tell us what is each angle with. Okay. Then we can go to the next question. So what does it say? Well, in the next one, they say, well, we now know these two angles are 90 degrees. So we can choose to erase this to get more space. How's that? So instead, we can just mark this and mark that. We know they're 90 degrees, that's fine. Okay. The next question says we need to prove that DF times BC will be equal to AB times BD. This is what they say. And this is for 4 marks, that's fine. Now we know that we need to prove similarity here because we don't have parallel lines. So we don't hope to use the proportionality theorem as we saw previously. So if we divide both sides by BC, as well as by BD. Remember, it doesn't matter which order you do it. As long as you do it, that's what matters. Ultimately, you'll have something like this one. Okay. If I look at this vertically, does triangle BDF exist? Yes, it does. Does triangle ABC exist? Of course it does. Well, that's nice. I'm just going to go on and mark these two triangles. The first one is BDF. In other words, this is my BDF there. And the next one is going to be ABC, so it's the entire triangle. Well, I'll just leave it that one. It's the big one. That's fine. So now we begin with saying, in triangle ABC and in triangle BDF, what is happening? Well, something interesting is really happening here. What is that? Well, I can actually see that both of them, oh, I nearly lied to you. What a big lie that would have been. Okay, we have already seen that two angles are equal to each other here. And what are those two angles? That's angle C, as well as angle ABF, the ones we have proven already. So angle C is indeed equal to angle ABF. It's already been proven. We just need one more. So what is that? Well, the term called theorem is going to assist. And is it? No, it's not. No, it's not going to assist. No, we can't use the term chord. However, we can use the following fact. What is that? Here we can see that angle D2 is actually equal to angle B2 because they are angles opposite equal sides. We have an isosceles triangle in this case, and the base angles are equal to each other. They told us that DE is equal to BE, which means angle B2 must be equal to D2. But if you look at D2, it is in the pink triangle. And if you look at B2, it is actually in the black triangle like that. So yes, we are right to say that. So then this means angle F in the smaller triangle must be equal to angle A because of the sum of interior angles of a triangle. So yes, that's what we say. Then now we can say this means the two triangles are indeed similar to each other. And we purely use the angles in order to prove this. That's awesome. Then now it's time to write down the proportionality. Well, we already did it down here. But the question is it total? Of course it is. Because I know that this angle is opposite that, and it's equal to this. So I have BD, I also have BC. Yes, it's definitely there in what I want to prove. Just not necessarily in the order that I have in my bottom part there, but that's fine. So I say BD in the smaller triangle divided by BC in the bigger triangle must be equal to what? I remember what I'm hoping to achieve. I'm hoping to have AB somewhere down the line. So it means in my next selection, I have to go to AB. Where is AB anyway? Well, it's opposite the 90 degrees. And this one is also opposite the 90 degrees. So I take my DF and then I say, well, this is divided by AB. Yes, that's the right one they asked me to prove. And then, of course, I'll tell them it's because these triangles are similar to each other. Then I can now cross multiply and do the thing. So when I cross multiply here, I can now ultimately say, if I take BD and I times it by AB, I'm just going to get the same as when I take BC and I times it by, yes, DF. Just that in the answer, this one occurs on the left and this one occurs in the right in what they asked you to show, but it's still the same thing. So yes. So then, knowing what we know, the next question says we need to prove that the point E is the midpoint of a circle that passes through the points D, B, and F. In simpler terms, how do you prove that a point is a midpoint in the context of a circle? Well, they're actually saying prove that E is the center of a circle. But this circle is passing through D, B, and F. So, yes, D, B, and F. It's got to pass there, you know? And it will pass there. And guess what? It did. So, yeah, more or less. Right. So what we need to do here is to prove that E is the midpoint of this circle. In other words, we need to prove that E is the center of the circle passing through B, D, and F. All right? Now, how can we show that a point is a center? We know many theorems regarding the center. The angle at the center is twice the angle at the circumference. That's one thing we can try and prove. We can try to prove that the line from the center perpendicular to the chord bisects the chord. But in this case, we don't have that line from the center because this is the center. So we can't say this line is the line from the center. You're lying. It's the line from the circumference to the center. No, we don't say anything about that line. It's just the radius. Anyway, it's not perpendicular to this tangent. So no. Many theorems with regards to the center, right? But the easiest one we can prove here is angle at the center equals twice angle at the circumference. Why? Because we can see that this chord is going to subtend angle E2 at the center, and the very same chord is going to subtend angle D2 at the circumference. So if we can show that E2 is twice as much D2, then we are done. And as a matter of fact, we can do that. So we can tell them that, no, that's what we are trying to prove. Sorry, I almost lied to you. But this is how we can do it. If you look at angle E2, it is, as a matter of fact, an exterior angle of this triangle. Yes, of course it is. So I'll just make it visible to you. It is an exterior angle of this triangle, and we know that an exterior angle of a triangle is equal to the sum of the two opposite interior angles. So then you can say exterior angle of a triangle. But you remember something. You remember that D2 equals B2 because they are angles opposite equal sides, yes? But since you already said that, you can say proven, which means that where you see B2, you can choose to replace it with D2 because they are equal to each other. And you find that this will just be twice as much angle D2. Then you can now conclude and say, therefore, E is the midpoint of the circle. Well, maybe I should have written it in, I should have typed it instead of trying to do that. How's that? So let's type and see. Yes, you can now say E is the midpoint of the circle passing through D, B, and F. And what could be the reason for your answer? Well, you can say, I use the converse. Converse of what? Converse of angle at center equals twice as much angle at circumference. Yes, you're not lying when you say that. You use the converse of that theorem, and that's how you proved that this is indeed going to be what you say it is. So, yes. Okay. So yes, Njapa just told us something that is important here. Another way in which we could have proven that this point E is the center, it's by using the converse of angles in a semicircle. Because now we know that this angle is 90 degrees, yes? And if this angle is 90 degrees, then it means this line is the diameter. And therefore, E has to be the center of the circle. Yeah, no, that's good thinking. Thank you, sir. Okay. Now, this is the same as the questions that whereby they'll ask you to prove that a certain quadrilateral is a cyclic quad. After you do that, you are now going through life understanding that the quadrilateral you proved above is cyclic, which means in the questions that follow, you are now going to use the understanding that E is the center of that circle. You have every right to use that understanding. You proved it in the previous question. All right? So that's what we'll be doing here. Now, what is this next question saying to us anyway? Well, it's 6 marks once again. They say, prove that 1 over BC squared minus AB squared is the negative of AD times FB divided by EF times AC cubed. Imagine, this is what they ask you to prove. You're not even 18 years and yet they ask you tough things. They might as well ask you to boost the economy of South Africa and create job opportunities. Well, that's the whole point of doing maths anyway. Okay, so what are you going to say here? Well, I know this one looks challenging, but it's not a problem at all. Because we know that when we see something squared, plus or minus, the first thing we think about is the theorem of Pythagoras. And in this case, it is possible to do it because we have right-angled triangles, two of them. Where is BC? Well, BC is in the bigger one. Where is AB? In the bigger one. So AC squared is also there. That's not a problem at all. Our problem, well, you won't see the problem until you look for it. This is where the problem is going to arise in these ratios. Because remember, you have proven two triangles to be similar. In the third question, yes? Was it the third question or it was the second question? So now we need to go to this ratio here and say which sides in this ratio are there in what they are asking us to prove. Let's forget about this. We can easily find that. The question is AD here? No, we don't have AD here. That's a negative. Is FB here? Well, FB is the same as BF. So yes, we do have BF there. Do we have EF here? No, we haven't got EF. It's a problem. And do we have AC here? Of course we do. All right. Now I want you to realize some things here. We are now using the understanding that A is the center of the circle, which means DE and EF are the radii of this circle. It means when you see DE, you see EF. Do I have DE here? No, I haven't got it. That's fine. Also, if you look at your AB, you can actually write it as AD plus DB. Or you can say AD. No, I'm lying. Or you can say AB is twice as much AD, or AB is twice as much DB. Do I have AB here? Of course I have it. But do I have it here? No, I don't. But I can come up with a DB or an AD. Okay. I know we cancelled this AD, but now we can see that, yes, we can work something with that AD of ours because we can express AB in terms of AD. Definitely something can work out. Okay, we said we don't have EF, but now we can see that EF is actually equal to BE once again, in addition to being equal to DE. So BE and DE, both of them are not present in the ratio that we proved here. Okay, well, that's fine. But at the end of the day, this is how we begin. We begin by stating our ratio here. But once again, we need to choose two because we can't take all three of them. Let's go and investigate BDBC so that we can see if we have to drop it or not. Oh, BD, there you are. BC, there you are once more. Okay. We can express our AB in terms of BD once again. Yes, we can do that. This one of DF. What is DF anyway? No, DF is very important. We can't leave it out. Okay, this is my vote. My vote is we need to take this ratio. So let's formally write it here on top. Then we say DF divided by AB is equal to BF divided by AC. That's how we begin it. Okay, fine. Now you can give a reason. That's because the two triangles are similar to each other. That's fine. Now we come back and say, we don't have AD here. So let's come up with a plan to eliminate what? AB. So this is what we can say. We can say, okay, fine. AB is the entire length, which is the diameter. But yes, AB is the diameter, and the diameter is twice the radius. So I'm going to write it down. I say, but I know that AB is twice as much AD. Yes, or maybe you can write it in a nice way first. And what is that nice way going to be? Yeah, to convince them beyond reasonable doubt. Maybe begin by telling them that this one is equal to that one. AD equals DB. Because they are radii, which means that AB is twice as much AD, because that's where we want to get ultimately. AB is twice AD, all right? Now we have AD, which was not there before. We have managed to remove AB and express it in terms of AD. What about DF? Well, DF is the entire length, and it's also the sum of DE and EF. So that's what you will say. You'll say DF is DE plus EF. Well, you didn't really need to say it like this. You could have just said DE equals EF. And once again, they are the radii as well. And then you can conclude and say, well, this means DF is twice as much, not really DF. Yeah, DF. Yes, DF is twice as much the one that you want to see, which is the EF. DF, which is the entire thing, is twice as much the one that you want to see, which is EF. So this is what you can say. Then go back to your ratio now and say, therefore, where I see DF, I can now put twice as much EF. And where I see AB, I can put twice as much AD. And then I can say this is equal to BF divided by AC. So you can say that. Just replace those lengths, which would ultimately mean that EF divided by AD must be the same as BF divided by AC, all right? Well, that's fine. Then the question is, do you still need to eliminate more sides? Well, let's go and check. FB, we have it there, both sides. AC, we have it both sides. EF and AD, we have them. No, we are happy here. Even though our AC is not cubed yet, but we are happy. We just need to get it in this form. So let's do that. How do we get it in that form? We cross multiply. So we have EF times AC, which is equal to AD times BF. Then we divide both sides. By what? You divide in such a way that you want to write it in this form. ADFB must be in the numerator. So you say, okay, fine. I'm just going to have 1 on the left-hand side. But on my right-hand side, I'm going to have ADDF, which you can choose to write as FB according to what you are given here. Then begin with EF and then times this by AC. Well, this is what you can say. Then where to from here? Well, easy. You are simply going to multiply throughout by the reciprocal of AC squared. In other words, 1 over AC squared, 1 over AC squared. That's what you will say. So that on the left-hand side, you have 1 over AC squared. But on the right-hand side, you have ADFB, EF, AC cubed. Then you remember the theorem of Pythagoras, going to the bigger triangle. You say the square of the hypotenuse, which is AB squared, it is equal to the sum of the squares of the two other sides, yes? In other words, BC squared and AC squared. And give a reason. It's the theorem of Pythagoras. You'll write it in full. And now you want to make AC squared the subject. So then AC squared is simply going to be, I want you to check. It's going to be AB squared minus BC squared, yes? However, according to how you want it, it's BC squared minus AB squared, which means you are just going to take negative out as a common factor so that BC squared becomes positive and AB squared negative. Then now you can come and say, okay, fine. Where I see AC squared, I can simply put negative into BC squared minus AB squared. And then this is now equal to, on the right, we have ADFB, EF, AC cubed. And the last step will just be multiplying throughout by a negative. And when you do that, the negative sign will just come and rest in front of this. And this is just what you are having. And you have indeed proven exactly what they asked you to prove. The most important thing in this case was expressing one side in terms of the other side. The radius is half the diameter. The diameter is twice the radius. That was the most important thing. And you see the sum of squares or difference of squares. Yes, right angle triangle. Definitely have to think about the theorem of Pythagoras, and you should be fine. Over and out.